Okay, so today we want to just establish, I guess, the basic properties of the derivative as a map between normed vector spaces, having last time basically spent the whole lecture trying to figure out what the definition was. So let's just recall the definition. So I'll kind of try and use this as a standard setup, that if I have a map, it'll be between normed vector spaces x and y. And then U is an open set in X, and F will be a function defined on that open set, taking values in Y. Sorry, then if you've got a point in A, if A is a point in U, we say the function is differentiable at A if there is a linear map let's call it T for the moment. I'll use this sort of calligraphic L to denote linear maps, or the space of linear maps between two normed vector spaces. That has the following property, that if you write F, so you can either write, sorry, this pen isn't very good, either write this in terms of sort of the value of the perturbation, like you see F of A plus H, which I think is what I did last time, or just write it as F of X is the value at A plus the linear map applied to the difference, plus then a quantity, which again, if you write this in terms of A plus H, you maybe define this as epsilon of H. So if you look at this equation, when X is not equal to A, this equation just tells you what this must be. So this whole quantity is the error in approximating f of x by this sort of affine linear thing. And I'm saying that the error after you divide it by the norm of x minus a is the quantity epsilon. Satisfies this error divided by the norm of x minus a goes to 0, which we just take as the definition of epsilon of a, that should say, as x tends to a. Okay, so it's saying that there is a linear map such that this sort of affine linear approximation to f is at least a better approximation to f of x than anything that tends to, well, than any error that is at least as big as the norm of x minus a. So this quantity goes to 0 faster, if you like, than the norm of x minus a goes to 0. Okay, and then if such a linear map exists, we call it the derivative. As I said last time, I think sometimes referred to as the total derivative to distinguish it from when you say partial derivatives. Of f at a. Okay, and we checked last time that, yeah, I think I'll tend to write, well, ideally I'll write with a pen that works at some point. Lowercase d or uppercase d, f to denote the total derivative, so, and then with a subscript for the value that you were taking the derivative at, just because this is a linear map, so we'll want to apply it to a vector. So having the point you're taking the derivative at as a subscript is slightly easier notation to read. Okay, sorry, yes, df at some vector v is just equal to the the directional derivative of f at a in the direction v. So this thing was a thing that was easier to define. It was just the limit as t goes to 0 of f of a plus t times v minus f of a all over t. So this directional derivative is the thing that you sort of get led to most directly from the ratio definition of the derivative in dimension 1. And where it makes sense, you get the notion of a directional derivative, but where the total derivative exists, it recovers for you all the directional derivatives just by evaluating that linear map on the direction in question. Okay, so I said this has sort of the standard properties of the derivative. So let's at least see the most basic of those. Okay, so suppose x, y, and u are as above, so x and y normed vector spaces u open in X. Then if you have two functions defined on u, and the derivatives of both exist at A, then the sum is differentiable at A, and its derivative is, you'll be shocked to learn, the sum of the derivatives. Okay, so there's a sort of, that's one of the kind of algebra of limits, maybe results that you might want for the derivative. Similarly, but a little bit more subtle, if you have, say, lambda defined on u, but taking values in the scalars, and f taking values in the normed vector space y, and you have the derivative of lambda. So the derivative of lambda is a linear map from the vector space u sits inside, which is X, to the vector space R. So it's an element, if you like, of the dual space of X. And the derivative of f is a linear map from X to Y. So this and the derivative of f at A exist. Then the derivative of lambda times f at A exists, and it's the derivative of lambda at A times f plus lambda times the derivative of f at A. And it's maybe worth just checking that syntactically this makes sense, right? This is a, as I said, linear map from X to the scalars. So certainly at any vector, you apply it to that vector and you get a scalar. You can multiply that by whatever f gives you at that vector also. And the same here. This is a scalar valued function, and this is a vector valued function, so it makes sense to multiply them. Okay, and then let's see. I think I had one more thing. Yes. The third point here is just, in a sense, to notice that the subtleties in the definition all really lie in the fact that the domain has dimension bigger than 1. So if you have a basis is a basis of Y, the target vector space, and let's say delta 1 up to delta n is the dual basis. So that's the basis of Y dual linear maps from Y to the reals. If the basis dual to By, then f is differentiable at A if and only if all of its coordinate functions are differentiable at A, and that's for all I equals 1 to m. Okay, so just to cash this out a bit more, if you write f of x in terms of this basis, you get some coefficients right? Every element of y is a linear combination of the basis vectors. Call the coefficients that you get, these are scalar valued functions, fi of x. Equivalently, fi of x is just apply the dual basis vector for bi to f. Okay, so this is and the statement is that this is differentiable precisely when its component functions are differentiable. And the derivative of the total derivative of f at a is just the sum of the total derivatives of the component functions at a times the basis vectors. So this just means, remember, this is a linear map, which is a map from x to the scalars. So taking the scalar that you get and multiplying it by bi gives you a vector in y, and the sum of those things is the derivative at a. Okay, so none of these things are particularly difficult to prove, which is what you'd hope if the definition was right. Let's take one. If f and g are differentiable at a, then what do we get? F of x is just the value of the function at a plus the linear map, which is the derivative at a, times x minus a, plus the norm of x minus a times an error. And similarly, g, sorry, get the same expression for g times some other error factor, epsilon 2, and we know that epsilon 1 of x and epsilon 2 of x tend to 0, which is what we define their value to be at 0, as x tends to a. Okay, so then just adding these two expressions, gives you that f plus g at x is f plus g at a plus the sum of the derivatives applied to x minus a plus the norm of x minus a times epsilon 1 of x plus epsilon 2 of x. Okay, so then this is exactly what we need in order for this to be the derivative of this, provided this thing goes to 0 as x goes to a, but that's just standard algebra of limits. Okay, so that's basically trivial, but it's just the model of what you have to do. So thinking about that for the second part, what happens if we take lambda, a scalar valued function, sorry, not on all of x necessarily, f, a vector valued function, then we know that if lambda is differentiable, I have this identity, and if f is differentiable, I have this identity, let's call it epsilon, where epsilon of x tends to 0, which is what we define epsilon to be at a, as x tends to a. And we want to understand how lambda times f behaves. Well, then we just have to multiply these two expressions together. But most of what you get is easy to control from what we already know about f and lambda, but there's one term that we have to think about. So lambda of x times f of x is then just lambda of a plus d lambda of a x minus a plus the norm of x minus a eta of x all times f of a, the derivative of f at a times applied to x minus a rather, and the norm of x minus a times epsilon of x. Okay, so we've got 3 by 3 is 9 terms to deal with. Lambda of a times f of a is the value of lambda times f at a. We want that one. Then you get lambda of a times df at a applied to x minus a. That's one of the terms I'm declaring is in the derivative of the product. And then I get lambda of a times this and that's not in what I was calling part of the derivative, but that's okay because certainly as x goes to a, this is the norm of x minus a times something that's a scalar times something going to 0. So this will go to 0. This we can put in an error term. What about the next factor? That gives us the derivative of lambda at a times applied to x minus a times f of a. That's the other part of what I was declaring the derivative will be. Then I get the product of the two derivatives, which again makes sense because this is scalar valued and this is vector valued. And that's the one that we need to think about for a second. But let's just write down everything else. We get that as the final term from that term, and then finally we get this times all those terms so let's okay, so now that's a lot of terms. If we gather things according to how we want them, this is the value of the product, then I get this term. Well, let me leave it like that. Okay, so those are the two cross terms that we got that are linear in x minus a. So that is the candidate for the derivative. And then I claim we have the norm of x minus a times everything else. Well, what is everything else? You get lambda of a times epsilon of x. From that term, we've got d lambda of a times x minus a, again times epsilon of x, which is this term. And then we have, I guess, all of these terms, which is eta of x times f of a plus eta of x times df at a, and then eta of x epsilon of x. Okay, so what we then the one term I've left out is the one which is d lambda of a at x minus a times df, the derivative of f at a times dx minus a. Sorry, df at a applied to x minus a. Okay, so now this term, this is going to 0, this is a constant. This is going to 0. This is a linear map applied to x minus a. So we know this is less than the norm of that linear map times x minus a norm. So this actually goes to 0 as x goes to a, and this goes to 0 as x goes to a, so the product certainly does. This goes to 0 and this is a constant, so they're both tending to 0 as x goes to a, or rather the product is. And then this goes to 0 and this is bounded. So this is bounded by the modulus of, sorry, the absolute value of this thing times the norm of the derivative times x minus a. So again, this is going to 0 and this is going to 0 as x goes to a. And then every term here is going to 0, so the product certainly is. Okay, so all of the things inside this bracket are straightforward to analyze, and it's just this that we need to think about, but we just use the same thing that we used here to see that if you look at, oh, sorry, I should have said, it's just plus this term, and we need to know that this term, if you like, divided by norm x minus a still goes to 0. So it's this divided by this. But I can look at, for example, just put the norm of x minus a inside one of the two linear factors, and you get this. So the norm of this is bounded here by just the supremum norm of lambda, because this vector has norm 1. And then this, using the same bound for a linear map applied to a vector, is bounded by the norm of the linear map times the norm of the vector. Okay, so we had the derivative of a scalar valued function multiplied by the derivative of the linear vector valued function, and the point is that if you divide by the norm of x minus a, you could put that inside one factor, and then the other factor is still going to 0. Okay, so it's basically just saying the product of two linear things has to go to 0, even after you divide by the norm of the vector going to 0. Okay, so the problem sheet asks you to essentially use the same argument to see that anytime you have a map in two vector variables that is linear in both, so it's a bilinear map, then the derivative, then such a thing is differentiable, and the derivative has the same form as it does here. Okay, so that tells you, if you like, basic algebra of limits. Things still work for this vector valued derivative. The other thing that I used in the sense that I argued you want it to be true of the derivative is that if a function is differentiable at a point, it is continuous at that point. Okay, so let's just check that is true. So suppose we've got a function on an open set in a normed vector space X taking values in a vector space Y, and the derivative at A exists. Okay, then let's say maybe for all epsilon greater than 0, let's just check. Yes, there is a delta greater than 0 such that the open ball of radius delta about A, where you shrink delta if necessary to make sure that sits inside U, is such that when you're within delta of A, the distance between f of x and f of A is bounded by the operator norm of the linear map, which is the derivative, plus epsilon times the distance between x and a. Okay, so in particular, the distance between f of x and f of a goes to 0 as x goes to a, because that's, of course, certainly true of this right-hand side for any x of distance at most delta from a. Okay, so this inequality is saying that the distance of f of x from f of a, provided x is close enough to a, is roughly bounded by the norm of the derivative of f at a, plus some error that you can make as small as you like. The thing to be slightly careful about is that this is not saying that f is Lipschitz near a. It's just saying that the distance between f at some point x and the distance between that, when you apply f to it, and f of a is bounded by a constant times the distance between x and a. But you don't know, for example, that if x and y are close enough to a, then f of x minus f of y is necessarily bounded by some constant times the distance between x and y. So that's the thing to be slightly careful about in the statement. Okay, so the proof is just rolling out this definition. We have f of x minus f of a equal to the linear map, which is the derivative applied to x minus a, plus the norm of x minus a times epsilon, where epsilon of x tends to 0, which is what we define epsilon of a to be as x goes to a. Okay, so that just means I can make the norm of this as small as I like, so long as I insist x is close enough to a. So thus, that's exactly what we need. There's a delta greater than 0. Chosen small enough so that it lies inside U. And when x is within distance delta of a, then that's better. The norm of epsilon of x is less than epsilon. Maybe this wasn't so great to call them both epsilon. I call this epsilon 1, perhaps that makes it easier to distinguish. Okay, but then for x in this ball, we have the distance between f of x and f of a is just equal to the derivative applied to x minus a plus epsilon of x times the norm of x minus a. So then we just use the triangle inequality and the definition of the norm of the derivative. So that's saying that the operator norm of the derivative times the norm of x minus a is at least as big as the norm of this vector. And then here, we bounded this by epsilon by the choice of delta. So this is bounded by epsilon times the norm of x minus a, which is exactly what we wanted. Okay, so that establishes that if you're differentiable, you're continuous. And I guess maybe just the thing to note is since f differentiable at A kind of, roughly speaking, means that f has a good linear approximation you should expect f is continuous at A if its derivative is continuous at A. So that's kind of the crucial point here. So if x is not finite dimensional, then we require that the derivative is not just a linear map, it's a bounded linear map. So i.e. a continuous. So if you like, the definition of derivative of a function being differentiable is that you have a good linear approximation. Again, I think the first problem sheet, so the way we constructed things, the values of the linear map, which is the derivative, are just the directional derivatives. So those are uniquely defined by the function. So if a function is differentiable, this gives you the values of the derivative at that point that you're asking it to be differentiable at. So the question of whether such a linear map exists, it's just an existence question. If it does exist, it doesn't mean the function is differentiable, as we saw last time, because the linear map can just be not a good enough approximation. If it is a good enough approximation in this sense, then this lemma, if you like, tells you that the continuity of f will follow from the continuity of its derivative, and then just in finite dimensions, that's automatic for a linear map. But if you work in infinite dimensions, it's not, so you just impose that as part of the definition. Okay, so the other, I guess, standard tool that you use when studying differentiable functions in one variable is the chain rule. And the way, in fact, the definition of the vector-valued derivative is set up, the chain rule holds for vector-valued functions with basically the same proof, actually. The only difference in the proof in the vector case is that we really have to use this lemma, whereas the corresponding statement in one variable, you barely notice that you use it. Okay, so the theorem is as follows. If you've got x, y, and z are normed vector spaces, and u in x and v in y are open, and you have a function defined on u taking values in y, and a function on v taking values in z, so these are just functions, such that such that f is differentiable at some point a and u, and g is differentiable at the image of that point in v, then the composition is differentiable at a and the derivative well, the derivative is the only thing it could, well, the only thing it sort of could be in the situation. Right, this needs to be a linear map going from x to z. You've got a linear map going from x to y and one going from y to z, given by the derivatives of f and g respectively. So the only thing you really have that you could use is the composition of those two linear maps. And the chain rule says that's the right answer. Okay, I just wrote the composition here. If you set it up in this generality, it's slightly messy to write down precisely what the domain of definition of this thing is. It's the intersection of the preimage of V with U. But if f is differentiable at A, it's continuous at A. And so that means if you're near B, your preimage is near A. And so since U is open, that definitely means that the composition is defined in some open ball around A, which is all you need in order to understand whether or not it's differentiable. Okay, so just to say that quickly, so since the f at A exists, hence G composed F is defined near A, since F inverse the preimage of V, so that's just the vectors in X, whose images lie in V, is a neighborhood of A. So in other words, it makes sense to ask if the composition is differentiable at A. Sorry, that's... Yeah, that's fine. So just what do we know in these situations? Just like in everything that we did in the lemma a second ago, you just write out what you're given. So f is differentiable at A implies that f of x is approximated by this affine linear thing plus the norm of x minus A times epsilon 1, a function from u to y, and g of y is g of b, which is f of A, plus the derivative of g at b applied to y minus b, plus the norm of that vector between y and b times epsilon 2 of y, let's say, where epsilon 1 of x tends to 0, which is epsilon 1 of A, as x goes to A, and epsilon 2 of y tends to 0, which is epsilon 2 of b, as y goes to b. Okay, so we want to understand the composition of G and F. So we just substitute in the first formula into the second formula, essentially. G of f of x is g of b, which is g of f of A, plus the derivative of g at b applied to, well, f of x minus f of A, plus the norm of f of x minus f of A times epsilon 2 of f of x minus f of A. Oh, sorry, just f of x. Okay, so now that's just writing y equals f of x. Now substitute in the first formula for f of x minus f of a, gives us the derivative of g at b applied to the derivative of f at a on the vector x minus a plus the derivative of g at b applied to epsilon 1 of x times the norm of x minus a, and then still plus this term here. Okay, so this is the value of the composition. Oh, sorry, that's an a, not an x. At the point A. This is the linear map applied to x minus a that we're claiming should be the derivative. So in order for that to be true, so thus the derivative of g composed with f at a is equal to the derivative of g at b composed with the derivative of f at a if, and only if, the error when you divide by norm of x minus a goes to 0. So that's saying 1 over norm of x minus a times this stuff goes to 0 as x goes to a. Okay, so there's two terms here, one of which is easier than the other. So it's enough, obviously, to check their sum goes to 0, to check that each term goes to 0. For one, we've got the norms cancelling. 1 is just equal to the derivative of g at b on epsilon 1 of x. And this is a linear map. Epsilon 1 is continuous at a. So as x tends to a, this tends to epsilon 1 of a, which is 0. So this is a composition of continuous maps. So it tends to its value the value of the composition, which is just the linear map applied to epsilon 1 of a, which is 0. So that's equal to 0. So that's the, if you like, straightforward one. The slightly more subtle one is this one. So 2, you've got the norm of f of x minus f of a divided by x minus a times epsilon 2 of f of x. Okay, now, if you look at this term, epsilon 2 goes to its value at epsilon 2 of b, which is 0. So this goes to 0 since epsilon y goes to 0 as y goes to b, and f of x goes to f of a as x goes to a, because f being differentiable implies f is continuous. Okay. So this term, the second term, we need to use the lemma that differentiability implies continuity. You need to both use continuity here, and then in this factor, so by the lemma, there's a delta greater than 0, such that if x is within delta of a, then this thing is bounded by the operator norm of the derivative of f at a plus 1, let's say. Okay, so we need to use sort of the precise statement of the lemma on continuity to show that this ratio is bounded by something, well, anything you like as close to, that's bigger than the operator norm of the derivative. And then this term goes to 0, so the product goes to 0. As required. Okay, so that proves the chain rule. And the proof is really just write down what you know and then look at what you need in order to prove the theorem. And that comes down to showing that you have this limit, and then seeing that that limit is indeed 0 for one term is sort of basically immediate from the definitions. But from the other term, you really need to use the argument that showed you that the derivative existing implies continuity at the point, and in fact implies something a little bit better than continuity, right? If f is continuous at a, it's not the case that the norm of fx minus f of a divided by the norm of x minus a has to tend to 0, well, has to stay bounded, in fact. Right? I mean, just take the square root function in the single variable case, and it's not true. And the reason, if you write out the proof of the chain rule from prelims, I mean, I guess maybe one hint that the definition of the derivative in higher dimensions is a good one is that what you do in that proof is you rewrite the one variable definition as the many variable definition, because the thing that's sort of subtle in controlling the chain rule is understanding sort of how the products of the errors actually behave. And you get a term just like this, but of course in the one variable case that's tending to f primed at a. And so you just have a factor that you know is bounded because it's tending to the definition of the derivative. Here you don't get that because the derivative is a linear map. So there isn't a single value of it at a, but you get roughly the same statement. You get that it's bounded, not quite bounded on the nose, but bounded by anything slightly larger than the norm of that vector. So the same, the same bound would hold if you use the absolute value of the derivative in the one variable case. Okay, wait, I feel, oh, yes. Just realized I forgot to prove the third part of the lemma. We proved the two algebra limit statements, but the statement that everything boils down to the one variable in the target proof we didn't do. So if we write, so proof of 3 in lemma. If f is given in this way, or sorry, the fi's are given in this way, so that fi of x is just delta I of f of x, delta 1 up to delta n being the dual basis, dual to b1 up to bm, I think I used, yep. Then if f is differentiable at a, applying the linear map delta I composed with f, is differentiable with derivative, the linear functional composed with the derivative of f at a. If you like, this is an example of the chain rule. If you have a linear map, kind of obviously the best approximation to that, which is linear, is itself. So if t is linear, t of x is t of a plus t of x minus a. Shows, I mean, on the nose, there's no error term. It shows that the derivative of t at a is just the linear map that you started with. So the derivative of this composition being this linear map composed with the derivative of f at a is a case of the chain rule. It's a much easier case, so you should just check that it follows immediately from the definition. Once you know that delta I is bounded, so you can use delta I of a vector is bounded by the operator norm of delta I times the norm of that vector. Okay, so one direction is trivial. If f is differentiable, then its components are differentiable. For the other direction, if delta I composed f is differentiable, well, what does that mean? It just means that fi of x is fi of a plus dfi at a applied to x minus a plus the norm of x minus a times some error where epsilon I goes to 0 as x goes to a. Then we can just add all these together. The norm of f of x minus f of a minus the sum of df I at a applied to x minus a times bi, that's just taking the components, minus norm of x minus a times the sum epsilon I of x times bi. So all I'm doing is I'm saying if you have this identity as scalars for one I equals 1 to m, take it and multiply it by the vector bi and add together what you get, and you get so this minus this, the value at a minus this in norm is just equal to this in norm. Right, so if you like, moving these two terms to the left-hand side shows that this sum is bounded by norm of x minus a times all of this, and then the norm of x minus a comes out. So let's just write that here. So this is equal to and then just the triangle inequality tells you that this is less than or equal to okay, and sorry, these are just scalars, so that's an absolute value. These are going to 0. As x goes to a, so this is just a finite sum of things going to 0 times constants, so it goes to 0. And that's exactly saying that the derivative of f at a is this linear map here, which is exactly what was in the statement. So if you know the components are differentiable, then the function is differentiable. So really, the thing to understand in the definition of the derivative is the case of x is higher dimensional, but y, the dimension of y is sort of not an issue. Okay, I think probably best to stop there for today, but next time we'll talk about partial derivatives and get some sort of fix for the fact that having all the directional derivatives didn't guarantee that you were differentiable. So the fix is just if you have all the directional derivatives, or even just the derivatives in the directions of the coordinates that you use, coordinate axes, and they're continuous, then you are differentiable. So, and then for the rest of the course, in fact, the condition of being continuously differentiable is always better than, well, it's obviously better than the condition of being differentiable in the sense that it's stronger, but it's the the one that's sort of the most robust. So functions that are differentiable can still behave slightly weirdly. Functions that are continuously differentiable are sort of the ones you can bring to a dinner party. They behave like you'd expect. Okay, and that's the main theorem of the course, which we don't actually prove, is the inverse function theorem, which says that if you're continuously differentiable and your derivative is invertible, then locally you're invertible also. Okay, so that's what we'll get to next week.